So welcome to the third part of this tutorial on how to construct indistinguishability obfuscation from well-founded assumptions. And I want to thank both of my amazing collaborators, Rachel and Amit, who also gave the second part and the first part respectively of this tutorial. Okay. So let me start off by defining the kind of recalling the overall picture that you saw from part one and part two. The overall picture was as follows. So in order to build IO, all you needed to build was a functional encryption scheme for NC0, satisfying a weak notion of security. And then Rachel told us that in order to build this, it suffices to build three simpler cryptographic gadgets. The first gadget is that of partially hiding functional encryption that you can build from Bilinear maps. And then the second part is the notion of homomorphic encryption for NC0 that you can build from LWE. And the third and the missing piece was this notion of weak structured seed PRGs, which in this talk, in this segment, I'm going to tell you how to construct assuming PRGs in NC0 and the learning parity with noise assumption. Okay. So just to summarize, I'm going to tell you how to construct structured seed PRGs from two standard assumptions, learn LPN over large fields, and then existence of PRGs in NC0 with polynomial stretch. Just for the sake of concreteness and setting up some notation, I'm going to recall these assumptions. So the first assumption is that of learning parity with noise. What does it say? It talks about indistinguishability of two distributions. In the first distribution, you're going to have n randomly chosen coefficient vectors AI, which are chosen from ZP to the L. P is a prime and ZP is a field. Okay, think of it being sub-exponential in the dimension L. And then you're going to sample n of them. N is some polynomial in L. Then I'm going to generate noisy linear equations, okay, with coefficients AI. So I'm going to sample a secret S at random from ZP to the L, take this in a product, then add it with the noise, okay? And this noise is going to be a sparse noise. With a large probability, it's going to be 0, but with probability L to the minus delta, where this delta is a constant between 0 and 1, I'm going to choose it to be random from ZP, okay? Then I'm going to add such a noise and do mod P and give out these n noisy linear equations to that adversary. So that's the first distribution. In the second distribution, I have just AI, the coefficient vectors, and then completely uniform uncorrelated values, UIs. And the goal of the adversary is to distinguish these two. Okay. An LPN assumption with parameter delta says that these two distributions are computationally hard to distinguish. Now let me make a few remarks. First, I want to observe a trade-off with delta. When delta is small, this assumption becomes hard because the probability of error becomes larger, right? When delta is close to 1, in fact, when delta is increased, the probability of error reduces and the problems become easy, so much so that when delta is 1, this is polynomial time broken. So that's the trade-off with delta. Now I also want to compare with this assumption with LWE. Those of you who have seen LWE before, this might sound pretty similar to LWE, but I want to stress in LWE, the error is chosen from a bounded integer distribution, such as a discrete Gaussian. Here it's a error, sparsely chosen error. So it's 0 with large probability with L to the minus delta, it's non-zero and random from ZP. So that's the comparison to LWE. And another thing I want to stress that throughout this talk, when I say computational indistinguishability, unless otherwise specified, I mean computational indistinguishability against sub-exponential sized adversaries. By that, I mean that there is some sub-exponential, appropriately chosen sub-exponential 2 to the lambda to the tiny epsilon, some constant epsilon, such that for any adversary running in time-bound that, these two distributions are hard to distinguish with a non-negligible probability. That's what I mean. And unless I clarify, I'll stick to this notion of indistinguishability. So that's LPN assumption. Just for the sake of parameters, I want to specify that for our work, we require delta to be an arbitrarily small constant greater than 0. So even if this assumption holds for delta equal to 0.0001, that's already enough for us to build IO. The second assumption we are using is an existence of Boolean PRGs in NC0. Boolean PRGs are length expanding objects. They take n bits of inputs and then they output m bits. where m is some polynomial in n. Think of it as n to the 1 plus some constant. We are looking for such PRGs implementable by constant depth circuits, meaning each output bit can depend only on a constant number of input bits, right? When it comes to security, we want that when x is chosen at random, g of x should look computationally indistinguishable to a random string of length m. That's just the traditional PRG cryptographic security. Um, Now I want to stress on some facts that I'm going to use. Main fact that I'm going to use is that it turns out that when you talk about Boolean functions which are implementable by NC0 circuits, they have a very nice structure. You can actually write any such function and therefore any PRG in NC0 as follows. Take any output bit yi from one of these m bits. Every such output bit can be computed um, by a by some constant degree multivariate polynomials where the coefficient comes from the integers and the polynomial is evaluated on the input x. So you can always write it as a constant degree multivariate real polynomial over the input x, each of the output bits. Okay, and this fact is a straightforward observation in analysis of Boolean functions. So we just want to keep this in mind because I'm going to refer it later in this talk. For concreteness, I want to specify that we are going to work with PRGs with the stretch of n to the 1 plus tau for an arbitrarily small constant tau greater than 0. So even if we have a PRG in NC0 with a stretch of n to the 1.0001, that's already enough for us to build IO. And in the first talk, Amit did talk about all these assumptions and gave you kind of the history of all these assumptions. So therefore, for this part, I'm going to skip on that. So what is this notion of structured seed PRG and what is about the structure that is useful for us? Well, what we want is that the PRG, whatever PRG we propose should be computable by bilinear maps. Okay, so they should be bilinear map friendly. And what do I mean by that? I mean, um, again, I'm not going to go into the formal definition until and absolutely I need it, but let me informally tell you what I mean. I mean that your PRG, each output bit should be evaluatable by a degree 2 polynomial, okay, on your input, where the polynomial is over the finite field FP, ZP, okay? So the coefficients are chosen from some ZP from some distribution, and each computation of the PRG output is a degree 2 polynomial um, over the input. Okay, so this is just an informal definition, and I'm going to formally define what I mean when I need it. Okay, um, so our work is not special in that it observes the connection between bilinear map friendly PRGs and IO. In fact, such a connection has been observed in quite a few previous works, starting from around 2018. So there's kind of already an established pseudo theorem. Again, I'm not calling it a theorem because it's not formally written down anywhere, but there's kind of an observation that is implicitly in all these works, which show that if you have a bilinear map friendly PRG, and if you rely further on some standard assumptions such as LWE or SXTH and assumptions like that, then you can build IO. Okay, so there was a strong intuition about that. And in this work, what we do, we construct another bilinear map friendly PRG, which we are calling structured seed PRG, from two standard assumptions, PRGs in NC0 and the Alpine assumption. So that's the main contribution. And then putting this PRG in the picture that I showed in very initially in the slide in this talk, that gives you IO. Okay, so I hope the picture is clear. So let me proceed. So for the rest of this talk, I'm going to look at this entire line that had evolved over past few years, just from the lens of bilinear map friendly PRGs. I'm going to tell you how they evolved over several years. And it's only in this evolution, what's so nice is that there's a feedback between the algorithms or the sum of squares community, which helped us to constantly refine these PRG notions um, and helped us immensely to build this notion of SPRG from standard assumptions. Okay, so now I'm going to talk about that history with an intention of slowly building you towards the solution of SPRG. Okay, So the first notion is a very natural one. Okay, in fact, if you see the definition, you will immediately connect why it's so natural. This is the notion of degree 2 PRGs. Roughly, they are PRGs which can be implemented by degree 2 polynomials over the reals, degree 2 multilinear polynomials. That's the rough intuition. So they come in two types. The first one were proposed by Lin and Tesaro. They are degree 2 Boolean PRGs, where the input sits in the Boolean hypercube, 0, 1 to the n. Their output is also Boolean. Later on in my work with Prabhanjan and Amit, and then concurrently Lin and Matt and Agarwal, we proposed this notion of integer degree 2 PRGs, where the input is an integer. So it's no longer sits in Boolean hypercube. It sits in minus lambda comma lambda to the n for some lambda. So it's an integer input. Your output is also an integer. But in both these PRGs, the evaluation has a nice structure. Each output coordinate is some degree 2 polynomial where the coefficients come from some appropriate distribution over the integers on the input E. Okay, so that's kind of the structure. And all these works show that if you have such PRGs, which this evaluation complexity, along with standard assumptions, that implies IO. And it's not surprising because these PRGs can actually be implemented by Bilinear maps. You can trivially see these are degree 2 polynomials. And that was just the key idea. And that was it. However, what turned out later was that just the fact that it has such a simple structure, this degree 2 structure, that was problematic. And if you're from algorithms community, you can already see it, but we were exposed to a devastating series of implausibility results. Um, the main culprit behind all these implausibility was this powerful hierarchy of convex optimization algorithms called sum of squares hierarchy. In fact, this is the same hierarchy which gives us best known approximation algorithms from many of the hard problems out there, such as the max cut problem, which is an NP hard problem. Okay. So when it comes to implausibility for degree 2 Boolean PRGs, this was shown because of applications of the symmetric version of Grothendieck inequality, which is derived from the sum of squares hierarchy. And then when it came to degree 2 integer PRGs, this was shown to be implausible due to another set of sum of squares algorithms, which are typically used in the context of matrix completion or matrix sensing. In particular, this nuclear norm minimization algorithm. Okay, so both these SOS algorithms led to implausibilities for degree 2 Boolean PRGs as well as the integer PRGs. And I want to specify that I'm calling it implausibility. I'm not calling it impossibility because it's not an unconditional ruling out of all parameters. Um, all these results actually work for a wide variety of parameters, but not every set of parameters. So it's not a complete impossibility. However, it was still, the parameters were still so general that it shook our confidence about this assumption. So that was the key thing. And because of that, the main takeaway that we as a community derived from this implausibility was that you want to avoid relying on PRGs where the evaluation is a degree 2 multilinear polynomial over the reals. So that was the kind of the takeaway. Uh, but um, if you think about it, it might already sound like a roadblock to you because throughout I was telling you that we need to build PRGs, which have degree 2 evaluations over the finite field. And now I'm telling you that PRGs which have degree 2 computations over the reals, they are problematic. So it might already sound like a roadblock to you. And the main problem was to construct something which escapes this set of computational model, degree 2 computation over the reals. And the main idea to avoid this came in this notion of degree 2.5 integer PRGs. Note that degree 2.5 is actually in double quotes because it's not a formal name. It was somehow unanimously accepted in the community, but there's a funny story about it. I'm going to tell you about this in just a while. Okay, and this was proposed in my work with Prabhanjan and Amit, and then follow-ups with Rachel Lynn and Christian Matt. Okay, so this was a clever idea which helped us to escape this model of degree computing PRGs over degree 2 polynomials over the reals. Um, let me tell you in more detail what roughly the structure looked like. So the input was going to be an integer vector. Okay, so it's going to be from minus lambda comma lambda to the n. So it's an integer vector, and your output is going to be a constant degree d greater than or equal to 3 polynomial. Okay, so it's no longer going to be degree 2. Okay, degree 2 were uh, broken using these implausibility attacks. Um, it's going to be degree 3 and up. This is very nice. So the previous attacks, they no longer apply, right? But then we showed that you cannot quite do this. We'll have to pay a little bit of compromise, and the compromise came at the cost of a leakage on the input. Okay, so there was a leakage on the input E from which was an n-dimensional integer vector. Let me now talk about how the leakage looked like. So just to recall, your input was n-dimensional vector over the integers. So the length is n. Therefore, the leakage will have n LWE samples of the form AI, AIS plus EI, okay, where the error for the ith LWE sample is exactly the ith coordinate of the input. Okay, so that's how the leakage look like. And this is over mod P. The LWE sample is over prime field P, where P is the order of the bilinear map. Okay, the order of the bilinear group. So that's how the structure look like. Now you'll ask me, why am I giving out this leakage? Well, the main idea is that if you ignore this leakage, of course, I cannot compute a degree 3 polynomial using bilinear maps because it's not a degree 2 computation, it's a degree 3 computation. But once I give out this leakage and encode these inputs E using LWE samples, then I can find a short seed, which is some function of the secret of the LWE, such that now when it comes to evaluating on this new seed, which is a function of the secret S, okay, these PRG outputs, they're going to be a degree 2 polynomial where the coefficients are some simple function of the LWE leakage that I've given out. Okay, so when it's seen as a function of this short preprocessed secret, you can do that, and that's what we show in this work. You can write this degree d greater than or equal to 3 polynomial as a degree 2 function evaluated on this new seed, where the coefficients depend in a simple fashion on this LWE leakage. Okay, so in essence, an adversary is only going to see this leakage, which has which is an LWE sample with error EI, and then a polynomial that is evaluated on the errors of the LWE, and it's a degree d greater than or equal to 3 polynomial. Okay, and this was nice. Now let me come back to the story. Why is it called degree 2.5? Well, the reason is that if I did not have leakage, then I would have called it degree 3 PRG. Okay, but then I have leakage, right? Therefore, it's not a degree 3 PRG, but it's not a degree 2 PRG either. So there's something in between. So that's why we're calling it degree 2.5 PRG. Somehow the community accepted it pretty nicely. Okay, so this was really nice. This escaped all the known attacks that applied previously. In fact, if you just ignore the leakage for the time being, the leakage over the finite field, the LW samples, then you can show some lower bounds for the same class of hierarchy, SOS hierarchy that came to attack the degree 2 PRGs. So you can show such lower bounds. So that was nice. And it's a reasonable assumption because some of Square's lower bounds, some of Square's programs as such do not know how to incorporate information over finite fields like ZP. So that was kind of the intuition. And when it comes to other algorithms that already existed, so far we do not know of any algorithm which meaningfully utilizes the leakage over ZP. The only known way in which we can incorporate these relations between the LWE as well as the polynomial evaluation is via these algebraic algorithms such as Grosvenor basis algorithms. But when you try to analyze those algorithms, turns out that those algorithms for the parameters that we use take sub-exponential time. So those attacks also don't apply. So then in a nutshell, none of the known attacks seem to apply. And that was nice. But still, it was unsatisfying. The reason is that it's a really new assumption, and there was an unusual leakage on the PRG input. So there's a polynomial, and there's an LW sample using the same input. Okay, this is as the error. So there's a cross relation. All of them are like jointly correlated. We do not know how to deal with this issue, how to utilize security of either of them to argue security of the total thing. And that was where we were stuck. Okay, we needed a way to decouple these two parts and argue security separately. That was kind of the whole point where we were stuck. And in this work, we construct this notion of structured seed PRG, which is also a degree 2.5 PRG. So there's going to be a leakage, and it's going to have a Boolean input and output. But this time around, we'll be able to prove security. That's the main point of our work. So just to give you a broad picture, our input will correspond to a Boolean vector sigma in 0, 1 to the n at random. So it's chosen from the hypercube at random. And then this PRG output, it's going to be nice. It's going to be a PRG in NC0 applied at sigma. Okay, and that's what we want, right? We want this PRG being applied on the sigma. But then recall that this is not a degree 2 PRG. PRG in NC0 will take at least degree 3 and up. Therefore, we cannot compute it using Bilinear map. We'll have a leakage. Leakage looks like this. It's going to be an LPN leakage. So there's going to be coefficient vectors AI. So n of them, where n is the length of the input. Okay, we choose AI from ZP to the L. P is the prime of the same prime as the bilinear map order. And then noisy inner products, AI and S. S is chosen at random. Plus EI. EI is a sparse error chosen according to the LPN error distribution. So it's non-zero with probability L to the minus delta. Plus sigma I. Sigma I is the ith bit of the seed. So this was the leakage. And this is what roughly the PRG look like. Now, again, just to recall, why am I giving out this leakage? We're giving out this leakage because, of course, you cannot compute the PRG using a degree 2 polynomial. It's not a degree 2 computation. But what we show in this work is that if we have a leakage like this, AI S plus EI plus sigma I, where EI is a sparse error, okay, then I can define a new seed, okay, which will be a short seed, which will depend on the secret of the LPN as well as the error vector, which is a sparse vector. Okay, but now you can compute this PRG as a degree 2 function over this new seed, where the coefficient depends in a simple manner on the LPN leakage. Okay, so that was the point. This sparse error helps you doesn't affect the evaluability. If the error is sparse, you can still evaluate it as a degree 2 polynomial on this new seed. That's the point. But what's so nice is that adversary only gets to see this PRG output and the LPN samples encrypting sigma. Therefore, you can argue security. Okay. We show in this work that you can prove that SPRG exists assuming LPN and PRGs in NC0, and the proof is really trivial. So Amit talked about this proof and gave a short proof in his talk. I'm going to just recall it on the next slide. It's a really short proof. Okay. So now just let me, on an abstract level, tell you why this LPN errors were chosen, why sigmas were encoded the way they are encoded using a sparse LPN error. The reason is, I've already told you that it helps you in evaluation, but when it comes to security, note that unlike the previous case where the same errors that are used in the leakage is also in the PRG part, the errors that are on the leakage no longer appear in the PRG part. Therefore, it gives you just enough independence in these two parts to argue security. So we will see that in the next slide. So here is the simple proof. You have a PRG output G of sigma, and you have these LPN samples encrypting sigma. Okay. Now, since the error doesn't appear in the PRG output, just by LPN assumption, you can replace AIS plus EI as uniform, right? And then I know that uniform over ZP plus sigma I is identically distributed as just uniform. So I can replace it with AI comma uniform and G of sigma. now I know that left-hand side has no information about sigma. Therefore, I can use PRG security to output a random string instead of G of sigma. Okay, and that's it. That shows that your output is pseudo-random, and that completes the proof. Okay, so there are minor subtleties which I haven't talked about, which I will talk about later about, but hopefully they are really minor and easily fixable. Okay, um, now let me proceed and tell you what's remaining. What's remaining is that I want to show you that you can implement it using Bilinear maps. And then I also want to tell you what exactly implementation by Bilinear maps mean. Okay, so there are two things that I want to tell you. So now let me talk about these aspects. So I'm going to recall the definition of SPRG. I know that Rachel did it in part 2, but for concreteness, I would still go over it just for the sake of formalism. So just recall, what is a structured seed PRG? It's a PRG with a structured seed. This is roughly the intuition. So it has following algorithms, like any PRG candidate. It has an index sampling algorithm, which takes two parameters. First parameter is lambda, which is a security parameter. It controls the level of security. The second parameter is n, which is the length parameter, which controls the length of the input. Okay, and think of n as some arbitrary polynomial in lambda, arbitrary large enough polynomial, and outputs an index. Okay, then the seed sampling algorithm takes in this index, it outputs a seed, and now here is where it differs from standard PRGs. Your seed is not traditional random string of length n. Now the seed can be seen in general to have two components, a public part of the seed and secret part of the seed. Okay, and public part will be revealed to the adversary, secret part will be kept hidden, and they might have some correlation between these two. Okay, so they're not standard like random strings. And the size of the seed is n times poly lambda, and remember n was the parameter that controlled the length, so that's the size of the seed. The evaluation algorithm is going to take this seed and it's going to output a string of length m. Okay, so that's the evaluation. Now, just to connect the dots from the previous slide, you should really think about this P, the public part of the seed, to be consisting of LPN leakages encrypting sigma. Okay, sigma was the input to the PRG in NC0. And your evaluation will just be G of sigma. This is what you wanted. Okay, this was just connecting dots. Now let me talk about what properties we need from the structured seed PRGs. We want that should have expansion, meaning the length of the output bits, the output length should be much more than the length of the input. That's what we want in expansion. Then when it comes to modeling security, it's a straightforward modeling extension of security of standard Boolean PRGs, where you are also leaking out the public part. So formally, given index and the public part of the seed, the output y looks indistinguishable to the index, public part, and a random string chosen from 0, 1 to the m. That's the security. Now comes one of the main points. What does it mean that to be implementable by bilinear maps? And this is what it means. We want that when you look at each output bit, yi, that should be that you should be able to write it as a constant, some constant degree polynomial, okay, over the public part of the seed and the secret part of the seed, with the restriction that it's just degree 2 over the seed. Okay, and this polynomial is computed mod p, where p is the order of the bilinear map. Okay, so over zp, really each output coordinate should be a constant degree polynomial, multivariate polynomial, which is degree 2 in the seed. Okay, and Rachel did talk about this. I'm just trying to recall it for sake of concreteness, just to remind you what is the model that we want. And there's a nice intuition why this can be implemented using bilinear map, because bilinear map are good at hiding degree 2 secret computations in the exponents. And note that this model, each polynomial is just degree 2 over the secret part of the seed. Okay, so and that's kind of the intuition why it can be implemented using bilinear maps. And we are looking for constant degree polynomials, which is just degree 2 in the secret part of the seeds. Okay, so let me now proceed and tell you how to construct such PRGs. So this is the desiderata. This is what you want. Okay. Um, so your index is going to be n randomly chosen coefficient vectors AI. Okay. And your public part of the seed, this is what you would expect. It's going to have LPN leakages encrypting sigma. Okay. Just to remind you, errors EI are chosen from error distribution of LPN. L to the minus delta is that probability of error. Okay. Sigma has length n. It's a Boolean string. And PRG is a PRG in NC0 with a stretch n to the 1 plus tau. Since it's a PRG in NC0, therefore it can be written as a constant degree D multilinear polynomial over the reals with coefficients in the integer. That's what I told you in the initial part of the slides. So it's a degree D polynomial over the reals with integer coefficients. It's a multilinear polynomial. Okay. Now the goal is the following. The goal is that you want to find a private part of the seed, okay, a private seed S, such that it is short, so it's small, much smaller than the output length. Okay. In fact, the combined length of the public part of the seed plus the secret part of the seed should be much smaller than the output length. Secondly, we want that this computation G of sigma, which is the desired value, okay, you should be able to compute it as a degree 2 polynomial over the private part of the seed, following the model that I just described. So it's constant degree over the public part of the seed and the private part of the seed, such that it's just degree 2 over the secret seed. Okay, that's the goal. Now let's see, why is encoding a leakage like that helpful? The key idea is that just because the error is sparse, it already kinds of leads you to compute, um, have a really nice candidate for private seed, which already gives you a very nice approximation to G of sigma. What I mean is that, let me propose actually the solution, a candidate solution. So I'm going to come up with, so I'm going to look at the secret S, which is used in the LPN. Okay. Then I'm going to pre-process all degree by D by 2 monomials over the secret. Okay. All at most degree D by 2 monomials in S, where D is the degree of the Boolean PRG when written as a polynomial over the reals. Okay. So I compute these monomials and put it in the private part of the seed. Okay. Now, one question that may arise, you might think that it's quite big, right? If the secret is big, then this might already be too big to put it inside the private part of the seed. But the point is, I'm going to set the dimension of the secret S to be small enough. In fact, I'll set this dimension L such that the size of the private part of the seed is actually linear in n. So it's okay. So I'm going to set dimension appropriately, and that will take care of the size of the private part of the seed. But then what it lets you do is that it lets you compute a polynomial like this. So remember, G was a multilinear polynomial of degree D or with coefficients over the integers. Therefore, I can also write it as a multilinear degree D polynomial over ZP. Okay. Now, when I write that polynomial, I can compute Y prime, which is G of B minus AS. Okay. So observe, this G is a degree D computation. So therefore, it's degree D in B. It's degree D in A. It's degree D in S. Okay. Now B is public and A is public, so therefore it's fine that it's degree D in B and A. But really the problematic part is that it's degree D over the secret S. Okay. But now note that I've already put in the private part of the seed all monomials in S up till degree D over 2. Therefore, it's just degree 2 over the private part of the seed. Therefore, it's a constant degree polynomial over P and S with degree 2 in the private part of the seed. Okay, so therefore it fits in the required complexity model. Okay, so that's nice. But now observe that this is exactly equal to G applied at this vector sigma plus E. Okay, so B minus AS is just sigma plus E. Remember, B is an LPN sample, and B minus AS is just sigma plus E, error plus the encoded, the secret um, hypercube input sigma. Okay, but now the point is that this error is really sparse. With L to the minus delta probability, it's non-zero and random, but with remaining probability, it's zero. Okay, and also observe that your PRG has constant locality. It's an NC0, therefore every output bit depends only on a constant number of input bits. Therefore, for every coordinate, every fixed coordinate yi from 1 to m, the probability that um, the desired computation yi, which is g of sigma, is the same as the computed value g of sigma plus e, which is y prime. This is at least 1 minus 1 by L to the delta to the power locality. That's the same as the probability that every coordinate that the output bit depends on uses zero error. So this is the probability, and by union bound, this is at least 1 minus order L to the minus delta. So what does it show? It shows that with really high probability already, every output bit is correctly computed, and only about, in expectation, L to the minus delta fraction will have errors. That's what it shows. The sparsity helps in the sense that it already lets you compute approximately the right output. Now the rest of the job is somehow to correct these m by L to the minus delta number of errors. That's roughly the idea. Let me formalize this. So I can define this set called bad, which is the set of indices where the desired output is not the same as computed output. Okay, then I can compute an expectation of the size of this set. Turns out that will be m by L to the delta, just utilizing the probability calculation that we did in the previous slide. It's m by L to the delta. And by Markov argument, this probability that the size of the bad is lambda folds more than the expectation is less than 1 by lambda. Okay, so with very large probability, at least 1 minus 1 by lambda, the number of errors are going to be less than lambda m by L to the delta. But with tiny probability, okay, 1 by lambda, I'm going to have more, I might have more than lambda m by L to the delta errors. Okay, so throughout this talk, we'll just assume that you want to fix m lambda by L to the delta errors. Okay, that's my goal for now. I'm just going to worry about fixing m lambda by L to the delta errors. And in with the tiny probability that the number of errors exceed this bound, then I'm going to just give up. I'm going to lose 1 by lambda in the advantage of security, but that's fine because security amplification and all those things, which Rachel also talked about, can take care of such things. Okay, so that's the goal. So now let's see, what can we do? So let me now define this object called correction vector. Uh, this is equal to the desired computation g of sigma minus the computed value of g of sigma plus e, desired minus computed. Okay, and observe that it's going to be t sparse. There are at most t non-zero entries in this m-dimensional vector, just because the size of the bad set that I was mentioning is bounded by m lambda by L to the delta. So it's a sparse vector. Now the goal is I'm going to utilize this correction. And what I want to compute this value y prime I, the ith bit coordinate, which is gi of sigma plus e that you can compute, plus correction entry I. So note that it just from the computation it adds the offset, and that by definition it's the right value. Okay, so that's my goal. And now I want to somehow put this correction vector in the private part of the seed by encoding somehow such that I'm able to do this computation. Now I want to observe that I cannot just put it straight into the private part of the seed as it is. The reason is that it's big. I mean, I know that correction is sparse, but if I just put it as it is without taking account of the sparsity, and it's an m-dimensional vector, and m is the length of the output of the PRG, and therefore I don't buy any stretch by just putting it there. So the goal is that I need to use the fact that it is sparse, somehow encode it in a short manner, put it in the private seed so that I can compute this computation. Okay, so let's try the first naive attempt. I mean, one trivial way you could do that. We know that the correction vector is sparse. Why don't I just put the non-zero entries in the correction vector in the private part of the seed? Okay, I can put just as it is. Uh, okay, and this is fine because these are m lambda by L to the delta entries. Okay, and this is much less than m. So that's fine, I can put it. And then somehow I'll reveal this set bad either in the index or the public part of the seed somehow, so that I'm able to do this computation. Y prime is gi of sigma plus e when I is not bad. When I is bad, then I want to correct it. That's my goal. But first of all, it's not clear how to do that using degree 2 computation. But even if I was able to do it, the main problem is I cannot reveal the set bad, because if I reveal it, I'm going to leak out which of the LPN samples have error and which ones don't. And that's detrimental to the security of LPN. So there's no security. So my goal for the rest of this talk, I want to compress this sparse correction vector in a way which does not reveal this bad. Okay. At the same time, it lets me do a degree 2 reconstruction as a polynomial and then add this correction to the computed output gi of sigma plus e. Okay, so let's try to see this with an example. For this example, let's assume that you just want to correct one error. So let's say correction is just one sparse, there's only one non-zero entry. Hmm? Now, the idea is that we're going to use the fact that the correction is one sparse, and we are going to compress it using matrix factorization. We're going to take this correction vector, encode it in some matrix, then factor that matrix using matrix factorization. Now note that matrix factorization is a degree 2 reconstruction, right? So that's kind of what we're going to do. Let's see it in more detail. So assume your size of the bad set is 1, so only one error. Now what I'm going to do, define a new matrix of size root m cross root m. It's a blank matrix. And then I'm going to sample a bijection which maps your indices of the PRG output into this matrix. So this is an arbitrary bijection. I don't care how it's sampled. Okay, so maps output bits into the grid. Now I'm going to take this correction vector and map it using that bijection that I sampled and put it inside this matrix. Okay, but by definition, correction is one sparse. Therefore, this matrix that I found, this matrix M, which I just constructed, this is going to have just one non-zero entry. Therefore, it has rank 1. Okay, since its rank is 1, I can factor it as u times v, where u and v are in ZP root m cross 1. Length of this matrix is root m, the rank is 1, so therefore I can find u and v like that. Okay, and now you could already imagine what's going on. I'm going to put this bijection in the index, put this u and v inside the private part of the seed, and then I'm going to compute this. The ith output being this PRG evaluated at sigma plus e, plus I'm going to reconstruct this matrix M. How? It's just u times v, which is a degree 2 function. Then I'm going to query it at the index phi of I. Okay. Okay. And that's a degree 2 reconstruction. And note that it clearly doesn't reveal bad, the set of bad indices, because phi is independent of that. Right? So that's nice. It lets me compute as a degree 2 function. But let's see what happens to the compression. Observe that the size of the seed is the size of the public part of the seed plus the size of the secret part of the seed. The size of the public part of the seed is just n times log p. There are n LPN samples. When it comes to the private part of the seed, there are monomials. These monomials have a short size. I'd set the dimension of the secret S to be sufficiently small, so it's also order n log p. When it comes to these matrices U and V, they are proportional to root m because it's root m cross 1. The dimension of U and V is root m cross 1. So that grows with root m. Therefore, the whole thing is much less than m. Okay, so that stretch is good. And security holds because bad is not leaked. Phi is independent of bad. Okay. Now, the key takeaway from this is that this approach can be generalized to lambda errors. In fact, it can be generalized even to say m to the 0.49999 errors. Okay. The reason is then it will yield m to the 0.4999 rank matrix. Therefore, the size of u and v will be like m to the 0.9999 something. Therefore, that's also much less than m. So we can handle up to about m to the 0.49 errors. But in our case, actually, the number of errors that we need to handle is much more than that. It's something like m lambda by L to the delta. Okay, it's only a fraction less than m. So we need to improve on this idea. And in fact, that's what we did. We extended this idea. This extension is as follows. So imagine there are t errors, which is m lambda by L to the delta. Instead of one bucket, I'm going to have t small buckets. So m1 through mt, there are t matrices, blank matrices to start off with. And every matrix is of dimension L to the delta over 2 times L to the delta over 2. Therefore, the total number of entries in all the matrices combined is m lambda. Okay, number of entries in each matrix is L to the delta, and number of entries in all the matrices combined is m lambda. Okay, so I just set up these T matrices. And my intention of sampling T matrices is that when I distribute these correction entries, each of them in expectation will have about a constant number of errors. Okay, that's my intention. So let's see. Let me sample this assignment function. I'm going to sample two maps. First map, both of them maps are random. Whereas in the previous example, the map, the bijection phi doesn't have to be random. Now it has to be for calculations to work out. So I'm going to sample two maps. Phi bucket, what it'll do, it'll map an index out of the MPRG outputs. It'll assign to a matrix, one of the T matrices. The second assignment function takes in the index and tells me which entry in that matrix does that index go to. Okay, so I just assigned two injective maps. Okay, and they are random. Now what I do, same thing. I'm going to take this correction vector, which has t non-zero entries. And then I'm going to use these maps and spread these errors into these matrices, M1 through MT. Okay. Now, in expectation, all of them are getting at most one error. But probabilistically speaking, we can show that with very large probability, almost close to 1 minus e to the power minus lambda, each of them will get at most lambda number of errors. And this is a Chernoff style calculation. It's a pretty standard argument just because of the fact that these maps are random. Okay, so all of them will get at most lambda non-zero entries. And now, since they are lambda sparse, the rank of them is less than lambda. Therefore, I can factor each of them as ui times vi, where ui and vi are in ZP root L to the delta cross lambda. So root L to the delta is the dimension, and lambda is the rank. Therefore, that's the length of the factorization. And I can factor this. Again, I'm doing the same thing. I'm going to put it in the private part of the seed, these ui's and vi's. Okay, and I'm going to put this index function phi, which has phi bucket and phi index, inside this index of the PRG. And then I'm going to compute a similar thing. Each output bit is this function gi of sigma plus e that you could already compute. Then I'm going to fetch the correction entry I. What is correction entry I? I'm going to look at matrix M phi bucket I, which is just u times v, the appropriate u times v, which is a degree 2 function. And then I'm going to probe it at the index phi index. Okay. And that way I can reconstruct correction I, and that's exactly equal to the desired output. Okay. So that's fine. And security wise, this is okay. Assuming less than capital T errors. Why? Because this phi function is independent of the bad set, doesn't reveal bad set. So only thing we are learning is the LPN sample encrypting sigma and the PRG output. Therefore, we can argue security, so that's fine. And it corrects T errors. Now, when it comes to stretch, this is slightly, we have to be careful at this point. So the size of the public part of the seed, there are n LPN samples, so that's n log p. Size of the private part of this seed S is going to have these monomials of degree d by 2. That we have already shown is proportional to n log p. The only new thing is the size of these matrices UI, and VI. So there are capital T matrices, and each of them have size root L to the delta times lambda. Therefore, the whole thing, the total size of the private seed, is something like m lambda square divided by L to the delta over 2 log p. Okay. So what does it mean? It means that since our L, the dimension is much more than lambda, okay, we can set it to be arbitrarily bigger than lambda. We have a fraction of L to the delta over 2 saving in size of the seed over the stretch. Okay, and turns out it's only this tiny amount of saving that saves us, and it's already enough to get us to IO, and that kind of concludes the stretch argument. Okay, so that's the overall picture. We get just a modest saving of L to the delta over 2. Turns out that's enough for us to build IO. And I've already showed how to prove it secure, but let me nevertheless spend a few more minutes. So what about security? So what we saw is that with very large probability, 1 minus 1 by lambda, uh, you only learn the Alpin samples encrypting sigma along with the PRG output. This is exactly the case when the number of errors are less than capital T, which is m lambda by L to the delta. Now with 1 by lambda probability, you might have more errors, but in that case, we were just giving up. So we are going to lose that security. Therefore, we can argue 1 minus 1 by lambda security immediately from LPN and PRG security in just the way that I told you. Okay, so this lets us construct weakly secure structure seed PRG, and then you have this overall picture which shows that once you have this weakly secure SPRG, you can go all the way up to IO. This is what Rachel talked about in the step 2. And that kind of concludes the overall picture. So that's it. That lets you get IO from these 4 assumptions. Standard assumption on bilinear maps, that is the S60H assumption, PRGs in NC0, LPN, and LWE. Okay, so yeah, that's where we are. So now let me just give you a few major open problems. One of the main open problems, according to us, is how to construct provably secure post-quantum secure IO from well-founded assumptions. So which in particular will mean that for our line of work, we'll have to remove this reliance on the bilinear map assumption S60H, because that's the only primitive, the bilinear map, that is um, known to be post-quantum broken. Okay, all the 3 other assumptions, they are plausibly post-quantum. So that's the only thing we need to do. Unfortunately, so far we seem quite far from that. Our techniques are very tailor-made for this direction. It's not clear how to get rid of the bilinear maps. However, there are some new directions that are emerging. In particular, they construct IO relying on strong and new circular security assumptions on fully homomorphic encryption, on specific fully homomorphic encryptions. These assumptions, however, they are new, but still they're considerably simpler from previous assumptions that were made. And we are hopeful that one day either this or some other direction leads us to this question of constructing provably secure post-quantum secure IO from well-founded assumptions. Another major open question, which is probably one of the most important question, can you construct something efficient that's implementable? Because that will have major impact in many of the settings. So here, there have been several works that have come up, and we are hopeful that one day we see more follow-ups on this efficiency question from well-founded assumptions, or even non-well-founded but simple to state assumptions. And finally, a simpler question that is simpler from the first question: are there any other approaches that yield IO from well-founded assumptions? Doesn't have to be post-quantum, but some other approach. Okay, so these are the 3 main questions, and with that, I would like to conclude. And I'd encourage all of you, if you have any questions, feel free to just email any of our co-authors to for these questions. Okay.